Uh, Anyone reply? Am I audible? And my screen is visible? Yeah, anyone? Just reply. Okay, fine. Thank you very much. Now, let us look at the divide and conquer strategy in this session. Now, this is the one of the topic of the second unit. In this topic, we try to solve a computational problem using a divide and conquer approach. Now, this is one of the approaches of solving a computational problem. A divide and conquer approach, or the strategy what we call, apart from the other strategies, this strategy uses a different kind of technique to evaluate and to compute or solve a problem. Now, as the name suggests, the divide and conquer approach, what we have is, we have a problem which is large. A large problem, let us call this problem as P. As the name suggests, divide and conquer. Let us first try to look at what is divide. When the problem is very large, the problem is divided into sub-problems. Like, for example, if we have a problem P, the problem P is divided into sub-problems, P1, P2, P3, so and so till K sub-problems. Now remember that when we call this problem and we say that it is divided into sub-problems, the sub-problems also should be of the same nature or same type. For example, if we have a problem, a large problem of finding from a collection of elements, finding which one is minimum and which one is maximum. So problem P1, P2, P3, that is the problem P is divided into P1, P2, P3, and these problems should be of the same type. P1 also should find from a small collection minimum and maximum. P2 should also find from a small collection minimum and maximum. So problems P1, P2, P3 are also problems of finding minimum and maximum. Now, these problems of finding minimum maximum is just an example. Let us take another example. Suppose if we have a problem P of sorting a collection of elements. So even P1, P2, P3 should also be sorting problems. They cannot be a different problem. For example, if I have P as a sorting problem, P1, P2, P3 and until Pk sub-problems, when we divide this problem, this P1, P2 should not be finding maximum element. Sorting means the problem, the entire set has to perform sorting itself. And one more important point is that these sub-problems, P1, P2, P3, whatever we have, we divide that. These sub-problems are non-overlapping. They do not overlap. For example, if I have a set of elements from 1 to 10, if I divide those elements from 1 to 5, so P1 will have 1 to 5, P2 will have 6 to 10. So they are non-overlapping problems. Now, what we have is, when we divide a problem into different sub-problems, what we have is what we say, conquer, is nothing but, we say that each problem, sub-problem, P1, P2, a small problem can be solved easily. So a large problem is divided into small problems, sub-problems, and each small sub-problem can be easily solved. So S1 is nothing but a solution to sub-problem P1. S2 is solution to sub-problem P2. Same way we have solutions for each sub-problems. Then the conquer part is when we have the solution to each of the sub-problems, we combine these sub-solutions, what we call, and we combine these sub-solutions to get the solution to the original problem P. So here P is the original problem, which is divided into P1, P2, P3, P till Pk, those are sub-problems. Each problem can individually be solved easily, and those solutions are as sub-solutions, what we call as S1, S2, S3 till Sk, and they are combined to get a solution as S to the original problem. Now suppose when we divide a problem P into a sub-problem P1, that sub-problem P1 can also, or sub-problem P2, P3 can also be large problem. So they can in turn be divided. So P problem P1 sub-problem can, if it is large, can in turn be divided into sub-problem, and their solutions can be found. Then those solutions are combined to get those solutions are combined to get a solution to S1, and finally we get the solution to the entire problem or the original problem. So here in this case, if you look at this part, that is the sub-problems, this part is divide part. And then when we have the solutions for this divide, we combine the solutions, that is we are performing the conquer approach, and that combining the solutions will give us the original solution. So this is what is the basics, or a basic theory about how divide and conquer approach works or strategy works. Now, obviously, every problem has its, to solve any problem, we have to have an algorithm. The same way, for divide and conquer approach, we have a general algorithm. Let us call this algorithm as D and C for divide and conquer, and P, we are passing parameter as P. P is nothing but a problem, a large problem. Now, once this divide and conquer approach, the algorithm is called, the very first thing we check is if the problem P is small. If the problem P is small, that means we can easily find the solution. That is, S is the solution here for the problem P, and we return this solution S. Now, else, if the problem is large, if the problem P is large, then we divide the problem. Remember that this is not specific. This is not specific to sorting or finding minimum, maximum, or merge sort, or any other application what we have. This is the general algorithm. So we divide P into smaller instances or sub-problems, that is P1, P2 till K, where K is greater than or equal to 1. Obviously, when we are dividing, it has to be greater than or equal to 1. Then we apply divide and conquer approach to each of these sub-problems. Which sub-problems? P1, P2, till Pk. Now remember here, we say we are applying divide and conquer. So what does this mean? This means that it will be a recursive algorithm. This is going to be a recursive algorithm. So we apply divide and conquer to each of the sub-problems. So this is P1 is again passed to divide and conquer. So instead of P, we have P1 here. Then if P1 is small, then we have the solution for P1. Else, again we try to divide P1. Over here we will have P1 into small instances like P11, P12, P13, and so on, P1K. Now, once this recursive call is made, even P2 will have its recursive call till Pk. Then once we have the solutions, that is S of P, we combine those solutions. So this is combine those solutions of divide and conquer of P1, divide and conquer of P2 till Pk. So this will give us the problem, for a solution for this problem, a large problem P. Now remember here, this algorithm is a general algorithm for divide and conquer. It is also known as control abstraction. Sometimes the textbook uses this word as control abstraction for divide and conquer approach. What we mean by control abstraction is that this algorithm, divide and conquer, just gives us the general idea of how to do it. It doesn't describe what small function does, what is the S function, that is the solution function, then how to divide those instances, P1, P2, P3, and how to, obviously this is a recursive call, so it will be same, and how to combine. So this functions what are used here, small, solution, combine, all these are abstract functions. These functions do not tell us what to do and how it is done. It just tells about that this is how an algorithm should work. So that is why we say abstraction. It's very abstractly it is defined that we have a problem as a small problem, then get the solution. Combine or divide the large problem into different problems, then recursively call and then combine those results. So they don't specify specifics. They don't give the specifics about what the how to solve that problem. And those specifics depends upon each and every problem which where we can apply divide and conquer approach. That is why it's called control abstraction. So this is what is a general algorithm for divide and conquer. Now, divide and conquer approach or strategy can be applied in binary search. This term you might be familiar with. Can be applied for finding minimum maximum elements from a collection of elements. Can be applied on merge sort. You might be familiar with this merge sort term. Quick sort, one of the sorting techniques, and merge sort and quick sort are the most efficient techniques of sorting a collection of elements. And it can be applied in selection problem. That is, here finding maximum and minimum elements is nothing but the same problem which we apply for the selection. That is, instead of finding maximum, minimum, we try to find in selection the kth maximum or kth minimum element. And then Strassen's matrix multiplication, the same divide and conquer approach is applied. Matrix multiplication you might be familiar with, which has several operations of multiplication and addition. Strassen's uses a different approach, tells us, gives us the way or tells us the way how to apply a large, how to multiply a large matrix. Then we have convex hull. This is one of the geometric problem that can be solved using divide and conquer approach. So these are the different problems that can be solved using divide and conquer approach. Now we will look at each of them and this the complete what do we call this unit. One of the part of this unit is that. Now before we move on to computing, to apply divide and conquer approach on different problems like binary search or sorting, so and so. Let us first look at how to find the time complexity, because this is one of the major things why we design an algorithm. We have to design an algorithm keeping in view or having the what you call complexities into consideration, and we need to have an efficient algorithm, or we need to devise an efficient algorithm. So here, let us look at how to find or how we can compute the complexity or performance of a divide and conquer algorithm. Again, if you see, we are using the control abstraction here. We abstract a divide and conquer algorithm we are using. We are not talking about any specific problem. Now here, if you see, the problem is P. The problem is of size n. That is n number of elements, what we call. That is the input, initial input for the problem. Now let us assume that divide and conquer approach uses or takes Tn time. T is time function. Like we have seen in the earlier classes that the computation of an algorithm is expressed in terms of functions, and depending upon what polynomial that function is, we try to say that the function takes O of n time or of O n square time, cubic or logarithmic or polynomial time. So let us assume that this divide and conquer algorithm takes T of n as the time. Now, if the problem P is small, obviously this is a primitive statement, it will return the solution to that problem. Now, we have already said, or in the earlier classes talked that primitive function, said that the primitive statements will take unit of time. The same way, if is a primitive statement, so it takes unit of time, we can, because unit of time is constant, we can ignore that. Return statement also takes a primitive time, but here S is a function which gives us the solution for the problem P. So we don't know what this S function is going to take, how much time it is going to take. So that is why we don't say that it takes primitive time, though it says return statement. Let us say that it takes g of n time, some function g of n time to give the solution. Then obviously else is also a primitive statement. Now here, dividing a problem P into small instances, even this might be a primitive statement. But let us say that this statement, or dividing a collection of elements, will take a time of f of n. So we are trying to represent the entire algorithm of divide and conquer, general algorithm for divide and conquer, using different functions. So let us assume that the divide function, the divide process of dividing a problem into subproblems will take f of n as the time. Then this function, this statement, apply divide and conquer to each of these subproblems. This is a recursive function. Applying divide and conquer, you are recursively calling it. So when you are recursively calling it, suppose P1, subproblem P1 has got N1 as the number of elements, or the size is N1 for P1, N2 for P2. So what is happening is, you can see P is size N. So recursively is P1 is called. This one we are saying, assuming it's N1 is the size of subproblem P1. So P will now be N1. So when we call this, what happens is, since divide and conquer takes T of n as the time, and this is a recursive function, so the first part will be taking, the first subproblem P1 will be taking T of N1. Then again recursive call is made to P2, so it will take T of N2. Assume that P2 has the size is N2. And so on till Pk, that is so on till T of Nk. Now this one is summation, because every time divide and conquer is called for each and every subproblem. So for each and every subproblem, this statement will be taking T of N1 plus T of N2 plus T of Nk as the time. That is the summation of the time for calling the divide and conquer for each subproblem. Then we have the return function, returning the combined one. This is a primitive statement. Return combine. Combine whatever solutions we have, we combine those solutions. So the entire algorithm, we have the time taken by the entire algorithm of divide and conquer, that is Tn. Tn will be equal to sum of Gn plus Fn plus Tn plus Tn2 plus Tn Tk. But here, what we have is G of this f of n and t of n and summation part will work if the problem is large, and return solution will work if the problem is small. So if problem is small, we have g of n. So here if you see, we have g of n if n is small. If n is small, and otherwise if n is large, whatever problem is large, it will be summation of T1 plus T2, or T of N1 plus T of N2 plus T of N3 till T of Nk plus F of N. So we will have plus F of N. So this forms the recurrence relation. Recurrence because we are recursively calling the function. So this T of N forms the recurrence relation for this divide and conquer approach. And always remember that the time complexity of the recursive algorithms are always computed using recurrence relation. Other algorithms, iterative and all, you will simply have the statements, you sum up those statements, and whatever polynomial you get, that will be the time complexity of that function. But for recursive algorithms, we will be using recurrence relation to compute its complexity, or time complexity. Now let us look at this. So here the generalized form of this problem. What we have over here is T of n. That is the time function. Same recurrence relation we have, g of n if n is small, and so T of n1 plus T of n1 plus T of n2 so and so plus T of f of n is otherwise. Now what we generalize, or what we say in general terms, is that this g of n is the time taken when n is small. We consider that n is the size of the input. And we consider that when the size of the input is small, means we say n, n is 1. So when n is 1, we say that the size of the input is very small, or the size of the problem is very small, and we can easily solve that problem. And when we say we can easily solve that problem, that means it will take unit time to solve that problem. So what happens is we can rewrite this T of n function, recurrence relation T of n equal to, when n is small means when n is equal to 1. So when n is 1, g of n, we say that it takes unit of time. What is that unit of time? It's T of 1. So when n is 1, so we say it's T of 1. Then otherwise means if n is greater than 1, if n is greater than 1, that greater than 1, we try to divide this n1 plus n2 plus n3, obviously is T of n, but we say that n1, n2, n3 is nothing but equally divided by some constant. So n1, n2, n3 will be n by 2, n by b, n by b, n by b, which is nothing but b is some constant. So summing up all these things, n1 is n by b, n2 is also n by b, n3 is also n by b, some constant b. We are trying to divide this problem using some constant b. So all these are summed up, and let us say they are a times we have the call to the recursive function. So T of whatever, T of whatever, T of whatever is a times. So we can rewrite this entire thing as a multiplied by T of n by b, where n by b is nothing but n1, n2. So every subproblem, the size of every subproblem, n1, n2, n3 is n by b, plus the remaining f of n, which is plus f of n over here. So this becomes the generalized form or reduced form for the recurrence relation of divide and conquer approach, where a and b are constants and f of n is the time taken by a function to perform the dividing approach, the time taken for dividing. And when n is equal to 1, the problem is small, which takes unit of time, that is T of 1. Now here, there is one more thing we need to remember, that when we are saying the input n is divided by some constant b, we generally assume that this n is b power k. B power k is nothing but k is the number of subproblems. So it's b power the number of subproblems, which is n. So generally we say that this is going to be some kind of, we try to usually we take b as 2. So when we take b as 2, so 2 means dividing every time by 2. If an array is there, we try to divide it by 2, again half, again half, again half. So 2 power k means if k is 8, that means, if let's say k is, let's say 4, 16, n will be 16. So 16 number of elements are divided into 4 subproblems. So that is what it means. So this is the general form of the recurrence relation. And we have to solve this recurrence relation, and obviously solving the recurrence relation, we will try to look at each recurrence relation when we look at the problem itself. So this was the general form of recurrence relations for divide and conquer approach. Now, so we're going to take up recurrence relation for each problem, and which uses divide and conquer strategy, and then we will try to solve that recurrence relation and find out what is the time complexity of those algorithms or those applications. Now let us look at the very first and the classical example of using divide and conquer approach. Now this is a binary search. You might be familiar with this binary search. Let us assume that we have these elements, that there are 1, 2, 3, 4, 5, 6, 7 elements in the collection, and we have to find an element. Now very first thing, if you observe that these elements are in sorted order, and binary search works only when the elements are in sorted order. Now let's assume that these elements are stored in an array, and we can represent this array with the name as A. An array will have its indices, and here we are starting the index from 1 because this is the algorithms which we are seeing. We are not talking about any specific programming language. So if you use programming language, then obviously if you use C, C++ starts from 0. So, but this is an algorithm, so let us assume the array starts from 1 till 7. There are 7 elements. Now the solution for this binary search problem will be to compute the mid value and check or search for the element if it is present in the mid index. If it is present, return the mid index, or we will check if the element is searching element, the element which we are trying to search is less than the mid element. Then we will search for the left half of the array, and we will not bother about the right half of the array. That is where the divide approach is coming into. Divide and conquer approach strategy works. Then suppose if the search element is greater than the key element, or the search element is greater than the element at the mid index, then we try to search the right half of the array, and we are not bothered about the left half of the array. So that is where the divide and conquer approach comes. So this is the solution. We need to consider 3 points. Then let us first, before we go on to see any algorithm, we will look at how this works. Now let us see that we are trying to search for the key 48, or the search element is 48. Now we will compute the mid index. So to compute the mid index, we need to know the start index. That is, in this case, let us say L as the left index, which is the start index pointing to the or referring to the first element. And let us try to take R index, which is the right index, which refers to the last element. Initially. So L initially is referring to the first element. R initially is referring to the last element. Remember, this is initial. Actually, L represents the left index, R represents the rightmost index. Now, to compute the mid value or the middle index will be floor of L plus R by 2. That is left index plus right index by 2. And then why we are using floor? Because the index or indices are always integer elements. And when we do something, when we divide something by 2, we may get a fraction or we may get a decimal point. So we take a floor value because we cannot have decimal as the indices. So here L initially will be 1, pointing 1, and R is pointing to 7, 7th index. So 7 plus 1 is 8. 8 divided by 2 is nothing but we get the result as 4. So mid will be pointing to index 4. Now is the element key, which is 48, we are trying to search. If key is equal to the element A of mid, yes, it is true. So we found the element. Now this is actually the best case scenario, that the element is found at the mid index, the initial stage itself. Now let us look at another scenario. 34. Let us look at searching an element 34. Now we start with L pointing to the first index, R pointing to the 7th index, the last index. So L is 1, R is 7, Mid value will be 1 plus 7 by 2, which is 8 by 2. Mid index will be 4. So mid will be pointing to 48. Now, is key, that is searching element 34, is equal to 48? No. Is it less? Yes, it is less than 48, the element at mid index. That is A of 4. So, this for 34, since it is less than 48, what we try to do is, we try to move the right index. We tried, key is less than mid element. We try to move the right index to mid minus 1. We are not moving till mid minus 1. So, right index is moved to mid minus 1. When it is moved to mid minus 1, the rightmost part of the array is not considered now. So we are only left with the leftmost part of the array. Now, why we are saying r equal to mid minus 1? What we had is, we had this entire set of elements as problem P. Now we have divided this into two parts. Let's say P1 and P2, but P2 we are not considering. And we said that the sub-problems are non-overlapping. They do not overlap. So we cannot take r equal to till mid. If we take mid, then obviously you have already checked this mid value. So what is the purpose of checking again? So we don't take r till mid, we take it as mid minus 1. And same thing will be with respect to L also. Now, then L is 1 now, R is 3. So 1 plus 3, which is 4 by 2, which will be index 2. Now, mid will now be pointing. This mid will now be pointing to index 2. Again, we check whether 34 is equal to 21. It is not. Is it less than 21? No, it is greater than 21. So key 34 is greater than A of mid. So what we do is, we move L equal to mid plus 1. So even here, if you remember, if you observe, L is mid plus 1 not equal to mid, because they are non-overlapping. And mid we have already checked. So now what happens is, L moves to mid plus 1. So mid was 2. So L moved to 3. And then the left part of the array is now ignored, not checked again. Then L is 3, R will be 3. So 3 plus 3 is 6. 6 divided by 2 is 3. So mid index will be 3 now. So mid will be pointing to element at index 3. Now 34 is checked. It is equal. So the mid index is returned, and we say that we found the element at index 3. So this is how binary search works, by applying the divide and conquer approach. And dividing here is trying to divide the array into left half and right half, and try to search only in one part of the array. Now suppose, 69 will also work the same way. Let us suppose it's only going to search for the right half of the array. And let us try to search for some element 36. Obviously, if you look at this, it's not found, but let us look at how binary search works. So L is taken as the first index, R is taken as last index. So L will be 1, R will be 7. So 1 plus 7, 8. 8 by 2 is 4. So mid will be 4. Now then 36 is not equal to 48. 36 is less than 48. So R index is moved to the right. So R will be mid minus 1. Now L is 1. R is 3. So 1 plus 3 is 4. 4 by 2 is 2. So mid index is 2. Now 36 is not equal to 21. It is greater than 21. So L will move. L index will move. That is L equal to mid plus 1. Now once this is done, the first time we have ignored the right half of the array, then now we have ignored the left half of the remaining subproblem. Then again L will be 1, R will be 3. L is 3, R is also 3. And now L and R, L plus R, 6 by 2 will be 3 itself, so mid will also be pointing to 3. Now 36 is checked. If 36 is equal to 34, no, it's not equal to. 30 is 36 less than 34? No, it is greater than 34. So if it is greater than 34, L is moved to mid plus 1. Mid is 3. L will now be 3 plus 1, that is 4. So L will move to fourth index. Now here at this point, when L moves, so even this element 34 we have checked, we have examined that part of the array, and no more elements are now there in the array to be examined. We have examined all the elements, then no more elements to be examined. So how do we know there are no more elements to be examined? When the index L crosses the index R. So when L becomes greater than index R, that means we have examined, we have divided the array into half, 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 so and so. And when L crosses R, when L is greater than R index, that means we have examined all the elements of the array and the element we are trying to search is not found. So when L crosses R, we say that the element or whatever key we are trying to find is not present or not found in the collection of elements. So this is how binary search works. Now, formally, a binary search is, the problem of the binary search is stated as, let AI be a list of n elements. AI means each one, where I is one between 1 to n. So there are n elements, I is 1 to n, A of 1 means 15, A of 2 means 21, and so and so, sorted in ascending order. This condition is very important. Sorted is ascending order. Otherwise, binary search will not work. Then the problem is to determine whether a given element X, whether the element X is present in the list or is present in the array. Solution would be, if X is present at A of j, that means A of j is equal to X, then we return the jth index, that is at this place it is found. That is what we are checking. A of mid equal to X, that is what we were checking. Now if X is less than the middle element or mid index, then search the left half of the array. Else, if X is greater than mid element, search the right half of the array. So this is how formally a binary search is defined, with the problem as well as its solution. Now, we said that binary search applies or uses divide and conquer approach. Now, divide and conquer approach has three things. First one is divide. Three phases actually. So first phase is divide. Now here in this case, in binary search, dividing is nothing but examining the middle element. And based on the middle element, we divide it. If it's not found, key is not found, then we divide. Conquer approach is to search the left or the right half of the array. Search the left or the right half of the array and then get the solution. Now in this case, combining is trivial because we don't have any result that has to be combined. We just, if it is found, we just say we have the solution, and then we just say we have the solution, and then we give the result, that is it is found or it is not found. So the three phases, that is divide, conquer and combine. Three phases of divide and conquer for binary search is to examine the element. Divide part is to examine the element. Search part is to conquer. That is, conquer phase is to search. That is, search either the left or the right half of the array. And combining is trivial because it's not found. It's trivial because if it's found, we return the mid index. If it's not found, we just say not found. That's all. We don't pass on the result with add up to some other result or merge somewhere, do something. So combined part is trivial. Now binary search can be solved using two different ways. One is the iterative approach. The other one is the what we call as the recursive approach. Now, divide and conquer, I said that it uses recursive approach. That's fine. It uses recursive approach, no problem. But using iterations also, iterative approach also, iterative way also, we can perform divide and conquer and get the solution for the binary search problem. So let us consider this same array, and we will call this algorithm as bin search, which takes in parameter as a, which is the array, n as the number of elements, and key which we are trying to search. And the very first thing I told you, L has to be initialized at the first index initially, R has to be initialized at the last index, that is R equal to n. Then we will use a while loop to traverse the array, to divide the array, and the condition is L less than equal to R. If L becomes greater than equal to R, that means L has crossed R index and there is no need to search the rest of the elements. So while L less than equal to R, we will compute the mid value, that is L plus R divided by 2. That is what we have seen. And suppose if the key is less than A of mid, then we will have R equal to mid minus 1. We will move R index to right. That is, if key is less than the mid element, that means it is going to be present, may be found in the left lower half of the array. It's less than, so obviously it's going to be in lower half. So we say R equal to mid minus 1. Else if the key is greater than mid, that means it's going to may be found in the upper half of the array. So we move the left index to mid plus 1 so that we only search the upper half of the array. Else, that means if key is less than, if it's key is not less than, if key is not greater than, then key must be equal to the mid element. So if key is equal, else if key is equal to, we just return the mid index. Now here, either the while loop returns the mid index and we say it is found at so and so, a key is found at so and so index, or L becomes greater than R and this while loop terminates. When this while loop terminates, we return 0. That means it is key is not found. So this mid while loop returns a mid index or will terminate. If it terminates, it will return 0. Otherwise, it will return the mid index. So this is how iterative algorithm works for binary search. Now this while loop now let us look at the different the analysis for this algorithm, binary search algorithm. Now L is 1 and then R is the last index initially. Now this while loop will execute till L until L becomes greater than R. Now this inside the while loop we compute the mid index. Now let us say that for analyzing this, let us try to construct a graphical representation of what the mid values are. All the mid values, all possible mid values. So first thing we found is mid value is 4. So there is a node. Let us say that this is going to be a tree, which 4 is the node for the mid. Remember, it's not the element, it's the index, mid index. So if key is less than mid index, then what do? We move R. We are only considering the left half of the array. Then we again while loop executes and mid index is computed. So now mid index is 2. So on the left side, because this is 4 is divided, now mid index will be 2. Then again if key is less than 2, then what happens is R again becomes mid minus 1. So R moves to index 1. And now again mid index is computed for the while loop. And then we have mid index as 1. So here we are trying to compute or calculate all the possible mid indices that can be achieved here, or that can be found here. Then what about after 1? Is there any value remaining after 1, after mid index 1? No, there are no elements remaining. So let us make this as the orange node. Let us represent this as external node. So after 1 there is nothing, that means. Now what about before index 1? Are there any elements? We have darkened everything. This darkened everything means before 1 also there are no elements, because if if you consider this element 21, it is at mid index 2. Mid index 2, we already have this node for mid index 2. So that is why the right side of the 1 also doesn't have any elements. What this means is, suppose if the element is we are trying to find is 10. When the element we are trying to find is 10, obviously after at mid index 1 it's 15. So 10 means it should lie before 15. So are there any elements before 15? No. That means 10 is not found. So any element before 1, mid index 1, we are saying it's an external node. This external node represents the element not found. The same way, if we have an element 18. Now 18 is greater than mid but less than 21 in this case, so and mid is 1. So it has to be greater than 1 but less than mid index 2. So what is greater than 1, less than mid index 2? This node. This node. So this node is again an external node, we are saying, and we say if 18 is the element, we say it's not found. So that is why we are trying to construct a tree of all the possible mid values that can be computed for this collection of elements. Now let us move forward. From index 2, it was if it is greater than the key is greater than mid element, then obviously here we will have L equal to mid plus 1. So L moves over here, and then we will have, again we will compute the mid value. Mid value is 3. So we will be having a node 3 to the right of node 2. And node 3 is left as null. Sorry, not null. There are no elements to the left as well as right. So we get the external nodes here. Then what about the right side? So everything to the mid index, every mid index to the left of index 4 is computed. Now let us see what is there on the right side. We have on the right side the element we have mid L moves to the mid plus 1, and we have 6 as the mid index. So there will be a node created to the right of node 4, so which has mid index, possible mid index as 6. Then again R moves if the key is less. So if the key is less than 6, then we have a mid index as 5. So we get the tree. The left child of mid index 6 is mid index 5. Then obviously for right of 5 and left of 5 there are no elements. And then if the key is greater than the mid, then L moves to mid plus 1. And now mid index will be computed, which will be 7 itself. So 7 becomes the mid index or the mid child of node 6. And there is nothing to the right and nothing to the left of 7 that needs to be compared. So this is how we create the entire structure or graphical representation, or we represent the entire computation of mid indexes using a binary tree. Now why this is considered as a binary tree or computed as a binary tree? Because every time we are dividing by 2, and looking at the left half or the right half at every stage. So that is why divide by 2. That is what is binary. 2 binary. Now let us try to analyze. What will be the best case? The best case would be if the element is found at mid index 4. That is at the first level itself, at the first computation itself, the element is found at the mid index. That's the best case. So best case, since it is done at the first instance itself, and first instance means when L is computed, R is computed. We have a while loop. Obviously, while loop will run for O of n times. But we have, this is a typical while loop. So when we enter the while loop, this while loop at the first instance itself at this mid place, it finds that the element key we are trying to search is equal to the mid index, and this is the best case. So while loop just returns the mid index at the first instance itself. While loop will not execute for n times or number of times. It only executes once. So we say best case is O of 1. Then let us compute the average of the worst case. Now, what would be the worst case of finding an element? Check mid index. If it is less, check again, then move to the next mid index, then move to the next mid index. So at the worst case would be trying to compare the element at the indices at every level. So there are 3 levels here. I mean, if you have large number of nodes, obviously the level of this tree increases. So the worst case is to search till the last, compare the element till the last level. So what is the last level? Last level is nothing but is the height of this binary tree, and height of the binary tree is log n. So when the height of the binary tree is log n, we say that at most log n comparisons we have to make. So the worst case of binary search is O of log n, because the log n is the height of the tree, and at most we have to make n number of log n number of searches, because till the last level we have to reach. Last level will be at height, that is the height of the tree, which will be log n. Now this is true for the worst case for successful as well as unsuccessful search. Even for unsuccessful search, that is nothing but the last level is all the external nodes which is represented by orange boxes. That is, element is not found at. So even for not element found or not found, we have to go to the last level in worst case. So in worst case, it is O of log n. Now, you may wonder that this is a while loop. While loop, it's a loop will run for n number of times. So instead of O of n, why is it becoming log n? Now, this while loop is not going to run n number of times. If you have n number of elements, each time the size of the elements are reduced by half. Every time by half. So that is why you can see that the tree, initially if this is n, this will be n by 2, this will be n by 2. Then this will be n by 4, n by 4, n by 4, n by 4. So this keeps on going. Every time it is divided into half by half by half and by half. So that is why that series of this, at this level it is 1, at this level there are 2, this level there are 4, next level there will be 8 nodes. So this is a series: 2 power 0, 2 power 1, 2 power plus 2 power 2, plus 2 power 3, plus 2 power 4, so on till 2 power n. 2 power n is nothing but log n. So that is, that series is nothing but log n series. So that is why this while loop will not run for n number of times, it will run for log n time. So in worst case, or even in average case, what we say is it's going to be O of log n times. So this is what is the time complexity with the binary search using iterative approach. In iterative approach, best case is O of 1, worst case and average case is O of log n. Now, there is another variation of the same binary search algorithm, which is given in the textbook. It uses low index instead of L. It uses high index instead of R. This condition is same. Low less than equal to high plus 1 is the condition. L less than equal to R. It's the same condition. It's no difference. Mid is computed same way. And then we check if it is less. If it is less, we make high as low. Uh, am I audible?
Yes, sir.
Actually, I lost my internet connection. So I joined back again once this was restored. So anyway, uh, I don't know at which place I lost the internet connection. So anyone can just um give me a hint that because I was just talking, I was just giving the lecture. I don't know when that I was lost. The connection was lost. So just kindly uh, give me a hint where I have from where to continue. Anyone? While condition of which algorithm, man? Bin search one. Oh, other algorithm. Very good. Thank you. Thank you very much. Okay. Now, am I presenting? No. I did it. Okay. Now here, this I suppose we were here. Okay. Anyway, this is the another iterative algorithm. So within the while loop, what happens is low and is less than equal to high minus one. Now here, remember that these two if statements, that is, if I less than a of mid and I greater than a of mid is checked over here, greater than equal to actually. Now here, high that is R and low that is L. We are not using mid minus one and mid plus one because high itself we have taken to be n plus one, just one more than the number of elements. So minus 1 and plus 1 is not needed here because high is one index more than the number of elements. Now this is actually a variation of the original algorithm itself. This is just for your information. Now what this is doing is this while loop is not returning any values. This while loop executes till low is greater than mid. It executes till that time. And then we try to check if is x equal to low. If it is low, that means we found that element at that low index and we return that low index. And then else we return 0. So what it is doing is, if you observe in the previous algorithm, we were having 3 comparisons within the while loop. This algorithm just reduces one comparison, and that within the while loop. So what we say is, if there are 3 comparisons, one extra comparison, then the number of time while loop runs, those many number of times that extra comparison has to be performed. So instead of that, to make it a little more efficient, though the complexity will be O of log n itself, but to make it little more efficient, one of the comparisons, which is whether it is found or not, equal to or not, is done outside the while loop. That is the only difference. But remember, for your exam or for your this one, for your any exam or any other evaluation purpose, this is the iterative algorithm you use. Don't use the bin search one iterative algorithm. Don't use this bin search iterative. This is only when a question is asked that how is iteratively a bin search performance can be improved, then only you have to go about this algorithm. Otherwise, the original algorithm, the one which we have seen, and which is called as bin search, this algorithm is useful, or you have to use this algorithm. So this was about iterative part of recursive search. Binary search, iterative part of binary search. Now we will look at the recursive part or recursive algorithm for binary search. Now, obviously, you all know L plus R. L is the left index, R is the right index. Let us call this binary as bin SRCH. You can use any name, it doesn't matter. Some places it's written as binary recursive or R binary search. It doesn't matter, you can use any name. So bin what happened? Again, I suppose I lost the connection. Is it not? Just anyone reply? Okay, where was I? Where were we? Having a lot of problem with this, I don't know. Where was I?
You started recursive algorithm, sir.
Excuse me, sorry, I could not hear you.
Recursive algorithm you started.
Acha, okay. Let me do it once more. Okay. Now this recursive. Very first thing we will check. We lost the connection and I don't know where I was. So let me just repeat it once more. I don't know whether it is repetition or also. Anyway, we will look at this binary search algorithm. The
So
first
you're
parameter.
not presenting the screen.
Okay. Screen is not. Thank you very much. Sorry. Uh, okay. Is it fine now?
Yes.
Okay. Thank you very much. Thank you. Now let us look at this binary bin search once again. I'm just repeating it. I takes first parameter as A, which is the array. Second parameter is L, which is the left index, and initially left index will be 1. Then we have the third parameter as R index, which is the right index. Initially right index will be N, that is in this case 7, and the key, which is the element we are trying to search. Now here, this is a recursive, and we say that this uses divide and conquer strategy. So in divide and conquer strategy, in general algorithm, if you observe, we had if the problem is small. Now in this case, binary search, the problem will be small when there is only one element left in the subarray. So when L is equal to R, that is when left index is equal to the right index, that means that there is only one element in the array and it is very easy for us to solve that problem. So when the problem is small, that means there is only one element in the subarray and we check if key is equal to that A of L, that element. Now here it can be A of L or A of R also, because they both are equal. If it is true, we return the L index or we can also return the R index. And if it is not true, that means element is not found. So this part of the F block is when the problem is small, when there is only one element in the array. Else, problem is large. We have to divide that problem. When we are dividing the problem, we use the same strategy, that is mid equal to L plus R divided by 2. Now, we have to either check whether the element is present at the mid index or not. Now, if it is present, that means here itself we have found the solution. At trying to divide the array itself, we found the solution and return the mid index. If the element x which we are trying to search, oh sorry, this should not be x, this should be key. This is key, sorry. This is key. What about here? Oh, here it is correct. Here it is problematic. Okay, no problem. Now, else if key is smaller than A of mid, that it is lies to the left side, then we recursively call the binary search algorithm. That is, this is bin search, passing A itself, that is the array, L index as it is, and instead of R index, we pass, you have seen in iterative, R equal to mid minus 1. So instead of R, we pass mid minus 1 here. Same strategy we are applying, same logic we are applying. Mid minus 1 and key will be as it is. If it is greater than, else means it's not equal, it's not less than, obviously it should be greater than. If it is greater than, then A is same, but instead of the left index, you might have, you remember L was equal to L plus L equal to mid plus 1. So instead of L index, we pass mid plus 1 index. and R index remains same and key is passed. So this is how recursive binary search algorithm works, or this is how we write the recursive binary search algorithm. Now let us look at the time complexity of this algorithm. Let us look at the time complexity of this algorithm. Let us assume that bin search or binary search, recursive binary search, the time it takes is t of n. Assume that this is t of n is the time it takes. Now this part, if part, is when the problem is small. And this whole part only takes unit time to compute, because all statements are primitive statements. Unit time to compute. Then, if the problem is large, we have the else part. In else part, mid is going to take, it's a primitive statement. If else returning mid value is a primitive statement, so they take unit of time. What about the else part? This else part will not recursively call binary search 2 times. It will not call binary search 2 times. The binary search recursively is called either on the left subarray or on the right subarray. It's not called 2 times. So this binary bin search, this return statement at line 14 is not going to take tn by 2, and return of bin search at line 16 is not going to take 2n by 2. If that happens, it will be 2tn by 2. But no, either this is a conditional statement, else if, else. Either one of them will be called, not both at a time. Next time it is called, then either one of them will be called, not both at a time. So this entire thing is going to take t of n by 2, because only half tn is for binary search. So time taken by this will be t of n by 2, because we are only working on the half of the input every time. So the recurrence relation, if we look at the recurrence relation, if n is 1, that means this part. If n is 1 is this part. If L equal to R is this part. L is 1. If it is 1, it is taking unit time to compute. That is t of 1. This is 1. Else problem is large, that is n is greater than 1, then it's tn by 2 plus, obviously this is going to be, or whatever constant you add, this is going to be f of n, which is 1. So anyway, if you have any number of constant, doesn't matter. We can just ignore all those values and only take 1 as the constant. So this forms the recurrence relation for binary search algorithm. Remember, this is the recurrence relation for binary search algorithm. Now we have we have seen a recurrence relation. That was a general recurrence relation. This recurrence relation is specifically for binary search. And we got this recurrence relation through the steps from our algorithm, from our binary search algorithm. Now to find the time complexity, we have to solve this recurrence relation. Let us look at how to solve this recurrence relation. Now here, this is the recurrence relation what we have. Tn equal to 1 if n is 1. T of n by 2 plus 1 if n is greater than 1. Now remember, we can solve recurrence relation in 2 ways. One is using the substitution method, or it is also called as a successive substitution method. And another method is to use Master's theorem. Now, Master's theorem does not work on all or every recurrence relation. It works under certain constraints. So let us look at successive substitution method, or it is also called as substitution method, to solve this recurrence relation. Now, what is the first thing we have? Obviously, if n equal to 1, it is 1. So we are not bothered about that. We are bothered about how to solve if the value of n is large. So T of n from our recurrence relation, T of n equal to T of n by 2 plus 1. So this forms the first equation. Let us consider this as the first equation. Now what we will do is, we will try to substitute in place of n. We will substitute n by 2, because on the next level the uh, collection is divided into 2. So we will try to create an equation where n will be n by 2. So we will substitute in place of n, we will substitute n by 2. So this will be T of n by 2 equal to T of this n is n by 2 divided by 2, and plus 1 will be of the original equation itself. So here we have T of n by 2 equal to T of n by divided by 2 is 4. T of n by 4 plus 1. So this becomes our second equation. That is T of n by 2 equal to T of n by 4 plus 1. Then we will try to find another equation. Let us substitute in place of n. We substitute n by 2. We got the second equation. We will substitute n by 4. That is next level. If you look at the tree, next level. So first level will be n. Second level it will be n by 2. Third level will be n by 4. Each element will be n by 4. So what we will do is, we will substitute in place of n. We will substitute n by 4. So when we substitute n by 4, so this n is n by 4 plus T of n by 2 instead of n by 4 divided by 2. So this will be T of n by 4 equal to T of n by 8 plus 1. Plus 1 is from the original equation itself. So this becomes our third equation. Let us go a further one step further. Let us calculate fourth equation also at the fourth level. So instead of we did it for n by 2, n by 4, we will do it for n by 8. So we will, instead of n, we will substitute n by 8. So it will be T of n by 8 equal to T of n by 8 by 2 is 16 plus 1. So this becomes our fourth equation. Now we will not go any further. We computed 4 equations just to have a clear understanding. Even 3 equations would have been sufficient. But to have clear understanding, we computed 4 equations. One with n, the other one with n by 2, third one with n by 4, and fourth one with n by 8. Now, we cannot go on further. Let us try to now use successive substitution method to get the answer. Now, look at here. T of n we have. You may, I mean, just follow the mouse pointer. We have T of n, which is equal to T of n by 2 plus 1. Now, in place of T of n by 2, we found the second equation. T of n by 2 plus T of n by 4 plus 1, second equation. So instead of T of n by 2, we will substitute the second equation, which is n by 4 plus 1. So it will be T of n by 4 plus 1 of this T of n by 2 plus 1 from the original equation. So this part is for T of n by 2. Then T of n by 4 can be substituted by the third equation. Here we have third equation. So T of n by 4 can be written as T of n by 8 plus 1 from the third equation, and then plus 1 is we have it over here, original equation. Then again in place of T of n by 8, we can substitute T of n by 16 plus 1. So here T of n by 16 plus 1, this part is for T of n by 8, then plus 1 plus 1 plus 1, 3 times. Plus 1 plus 1 plus 1, we have it from the original equation. So this is 3 times we have successfully substituted the equation. That is T of n by 2, T of n by 4, T of n by 8. Now, we cannot go on further. If you go on further, doesn't matter. You have to create a fifth equation, substitute that equation. It doesn't, I mean, there's no point in continuing. Now, what we have to do now is this term, that is t of n by 2, n by 4, n by 8, n by 16. The rest of the other terms are all constant. So this has to be computed till when? Assume that it has to be computed till ith time. Till ith time. So if it is continued till ith time, what we have, what we get? First time is 2 power 0. Second time, actually this is the initial uh, equation itself. First substitution we got, so this is 2 power 0. First substitution we got 2 power 1. Third substitution n by 2 power, sorry, first part is 2 power 1. Second substitution 4 is n by 4 is n by 2 power 2. N by 8 is n by 2 power 3, third substitution. Fourth substitution is n by 2 power 4, which is 16. So this way, for the ith time, what we will have is n divided by 2 power I. That will be for the ith time. For the ith time, it will be n divided by 2 power I. Plus, now each time, first time 1, second substitution 2, 3, 4. So ith time, it will be, so 1 I times. So 1 multiplied by I is nothing but plus I itself. So this equation, I mean, we got this equation for the ith time as t of n equal to t of n by 2 power I plus I. Now this t of, let us write it here, we use it here, t of n by 2 power I. Now what we have to do, what we say, is this problem, we divide it such that, we divide such that it reduces to a smallest problem. So what is the smallest problem? Smallest problem is when n is equal to 1. So when n equal to 1 means, if you look at this part, t of 1. T of 1 is 1. We know this 1. T of 1 is 1. We know it takes constant time. So when is t of 1? When n is 1. So this part should reduce. That is t of n by 2 power I should reduce to 1. So we can say that t of t of 1 means 2 power n by 2 power I is equal to 1. So when n by 2 power I becomes 1, we say it is t of 1 and t of 1 is 1 itself. We got the answer. So what will be n by 2 power I equal to 1? That will be equal to n equal to 2 power I. And that is nothing but I is equal to log of n base 2. N equal to 2 power I is I equal to log n base 2. So in this equation, t of n equal to, this becomes t of 1 plus I. Wherever I we have, we will substitute by log n. So we have, in place of I, we have substituted by log n. And t of 1, n is equal to 1. T of 1 is nothing but, we have the answer as 1. When n equal to 1, it is 1. So t of n equal to 1 plus log of n, which is nothing but, we can say that t of n, the function t of n, is O of log n. So in recursively, when we have computed its recurrence relation, and recurrence relation, we have applied substitution method, successive substitutions, we found the answer of t of n to be O of t of n to be 1 plus log n, that is the polynomial, which is nothing but, we can say that it is O of log n to base 2, or O of log n itself. So both with iterative method as well as recursive method, the complexity of the or the time complexity of the binary search is O of log n. So this is how we compute the time complexity. So this was all about the binary search. We have seen how binary search works. We have seen how what is the iterative algorithm for binary search, and we have taken a tree of mid indexes and then evaluated the complexity of iterative binary search. We have looked at the recursive binary search algorithm, as well as we have, using the recurrence relation, we have computed the time complexity of the recursive binary search algorithm. Now, so this was all about binary search and its complexity and how it works and what is the how recursive algorithm recurrence relations compute. So each time when each algorithm we see, if it is a recursive algorithm, we will compute its recurrence. We will find its recurrence relation and then apply a substitution method to solve that recurrence relation and get the time complexity. So this each recursive algorithm we will be finding the recurrence relation and its time complexity. Now let us look at another problem of finding maximum. Sorry, is it there in the syllabus? First of all, control action, merge sort, quick sort, binary search. No, sorry. Maximum, minimum is not there as part of the syllabus, so let's not go into it. Let us look at merge sort. Merge sort is one of the sorting techniques which is very efficient in terms of its performance. Now, merge sort uses merge sort actually as a term. Merge is there. We look at this, what this merge means or merging means. This merge sort uses divide and conquer approach. Now let us take the the elements here. We have 6 elements, and we have to sort these elements. So the problem to solve is sort the elements in ascending order. So I mean, mostly the term is used. Term uses non-decreasing order. It's nothing but ascending order itself. Now, what merge sort does is it splits the elements into 2 subsets, just like binary search. Split the elements into 2 subsets, and these elements are non-overlapping. Again, remember, they are not overlapping. Split the elements into 2 subsets. Each set is individually sorted, and then we merge these 2. When each set is individually sorted, that means we have 2 sorted sets. We merge these 2 sorted sets to get the original set, original sorted set. Now here also problem is large. We have to split that problem or divide that problem into small sub-problems and solve it. Now let us talk about the solution in terms of divide and conquer strategy. Now here 3 phases of divide and conquer is, first phase is divide. So n number of elements are divided into n by 2 elements. And here also it's divided by 2 itself, not by 3 or 4 or something. It's divided by 2. Merge sort always divide the elements into 2 subsets, divide by 2. So 2 subsets, that is what is the divide phase. Conquer phase is to sort the 2 subsets. And sorting those 2 subsets is nothing but when we have left subset and right subset, those 2 subsets may also be very large. So again, merge sort can be applied on those 2 subsets. And I mean, again, applying merge sort means we are recursively doing that. So conquer approach here is to sort the two subsets recursively using merge sort. Now, till when these two subsets, I mean, till when should we call recursively? We should call merge sort. The idea is here is that we have large collection n number of elements. We divide those elements into subsets n by 2, n by 2, such that at the end or until there is only one element remaining in the subset. And the idea of merge sort is that when there is only one element remaining in the subset, that means that element is already sorted. So that's the idea, to divide into subsets, subarrays, until there is only one element left in the subset. When there is one element left, it means that it is sorted. Then we have the last the phase as the combine. When we have two sorted subsets, merge those two. So merge, the term merge is coming from combine. Combine those two sorted subsets to get a sorted set or sorted original set. So that's the basic idea about merge sort. Now here, actual merge sort algorithm only can be completed in 3 or 4 steps. That's all. But the actual part or actual working of merge sort is in the combine phase, when we merge two sorted subsets. So we will first look at how to merge two sorted subsets. And this algorithm is known as merge sort algorithm. This algorithm is known as merge algorithm. And merge sort uses this merge algorithm. So the actual working or the main computation part is in merge algorithm. Now let us take these two subsets, or we say these two arrays, 31, 57, 84, and 25, 63, and 96. Now these two subsets, they are sorted, individually sorted, not combinedly, individually sorted. 31, 57, 84 is individually sorted, 25, 63, 96 is individually sorted. Let us call this as array, because element collection elements is stored in an array. Now actually, this is a single array. It's a single array. We are not taking two different arrays. It's a single array. This single array obviously is going to have its indices. Actually is divided. We say that it's divided into two parts. So here what we have is, we have low index starting from first index referring to the first index. We have high index referring to the last index, and mid index computed among these two. That is 6 plus 1 plus 6, 7 by 2 is 3.5. Floor value is 3, index 3 itself. So this array, for our convenience, the elements are in sequential order. There are no two different arrays. They are sequential order. But for our convenience, let us physically have a separation between these two. Now we will call this part as left subarray, this part as right subarray. Now we will take a temporary array. So what we are trying to do is, we are trying to merge these elements of the left subarray and the right subarray. To do that, we are using a temporary array known as B. This is a temporary. Now, we will have a variable h, which is pointing to low. We will have a variable I, which will point to index of 1 in the array B. Remember, it's array B. Then we will have another index as J, which points to the first element of the right subarray. It is actually index 4, but it's the first element of the right subarray. Now, The logic behind this is we compare the element at index h, which is the first element from left subarray, with the first element from right subarray. Whichever is less, we will try to store that in array B at index I. So h is first index, j is fourth index, element at index h is 31, element at index j is 25. 25 is less than 35, 31. So 25 is stored at index I. Then, which element we stored? We stored 25, which was referring by j. So this element we have stored in this array. Actually, it is not deleted. I'm just darking it so that to show that this element is completed. We have processed this element. Then j will move to the next. H is not moving, remember. So whichever element we stored in array B, the index of that element moves to the right. Then simultaneously I will be moved so that we can store the next element at index second, the next index in array B. Now again we perform the same step. Element at H, which is still the first element, is checked with element at J. Now the jth element, the second element of the right subarray. Now whichever is smaller, that element is stored at index I. And obviously 31 was stored, so we move J to the left, towards the right. Same thing happens, again I is also moved so that next element can be stored. Now element at H is compared with element at J. Which one is smaller? 57. So 57 is stored, H moves to the right. Again, I also moves to the right. Again, element at H is checked with J. 63 is smaller. So 63 is stored here. And then J, since 63 was stored, J moves to the right. Again, these two are, I also moves. Again, H is compared with J. H is element at H is smaller, that is 84. So 84 is copied to array B, stored at array B, and H moves. Now when H moves, it is not the blank thing. It is from index 3 to index 4, it is moving. Now when H crosses mid-index, then we stop. Obviously I is moved, then we stop. That means when H crosses mid-index, that means all the elements of the left subarray are stored in array B. There may be some elements, or may not be, some elements remaining in right index. In this case, it is remaining. It's not only one element. We can have so many other elements also remaining here. Doesn't matter. Or there may be the case that J index crosses. Or there may be the case that J index crosses high, H will be at mid, J crosses high. If J crosses high, that means there are no more elements in the right. All the elements of right subarray is stored in array B. There may be elements left in the left subarray, but in this case, it's the right subarray. So what happens is at I, we try to store all the elements from J till end. Now it's only one element, so there's nothing, just storing that element itself. If there are other elements, then I is moved, J is also moved, then J goes and all the other elements will be stored in array B. So this is how merge sort happens. This is how merging happens, not merge sort, merging happens. Now, once all the elements are compared and stored in the temporary array B, actually, we are merging whom? Whom are we merging? Two sorted arrays. And the result of two sorted arrays is a sorted array, which when we merged, is stored in array B. Now we have to copy these elements back into the complete array A. So what we do is we use a variable k. We use another way, that k variable is obviously pointing to first index of array as well as first index of array B. And then each element is copied back, moving, incrementing the index k. And then these two things are merged. Actually, when we copy it, that means it is merged itself. So we have separated for our convenience, we have separated by a space, just for our convenience, but it's actually, it is the same array itself, which we have, what do we call, separated, and which we have physically separated for our convenience, but it's this same array. So now you can find that the whole array is sorted. Now, just before we look at the merge sort part, let me clarify one more point here. That is the array B. What should be the size of array B? What should be the size of array B? The size of array B should be equal to the size of the left subarray as well as size of the right subarray. Now, left and right subarray is nothing but starting from low index to high index. So the size of the array B should be till high index. That is the size of the that is the size of the, what do you call, temporary array B. So temporary arrays B size will be till high index. Now, as we have seen this example, let us now look at the quickly look at the algorithm. So this algorithm is called as merge. Remember, this is not merge sort. This is merge algorithm. The heart of merge sort, actually. This is the merge algorithm. Merge algorithm takes three parameters: low, mid, and high. This is what three parameters: low, mid, and high. Low, we pass initially 1. High, we pass initially the nth element. Mid is computed using low plus high by 2. Okay. Then we have a temporary array. So what we have a temporary array, and then this merge algorithm takes a variable h, which is initialized to low, variable I, which is initialized to low itself, which will be pointing to array B. We'll come to this array, part of array B, and then there is a j which will be initialized to mid plus 1. So mid is 3 here, mid will be 4. So whatever mid is there, j will be initialized to mid plus 1. So h will be the start index of left subarray, j will be the start index of the right subarray. Then we have a while loop to check whether h is less than mid, less than equal to mid. If h crosses mid, that means all elements are done for left subarray. And j less than high. If j crosses high, that means all the elements of right subarray are completed. Now, these two things. Now, if a of h is less than equal to a of j, if this element is less than equal to this element, then b of I, you're storing in b of I equal to a of h. This is less than this, so store this. Else, and increment, obviously, increment the h part. Else, store j, this is small, store j in b of I and increment the j part. So if element of left subarray is small, we store that in b and then increase the h index. If element of right subarray is small, we store the element of right subarray in array B and increment the right index, j index for the right subarray. Now this happens. Now, and this, for once the condition is checked, obviously we have to move I also. So I is equal to I plus 1. That is, we are moving I. Now, this while loop continues till this h is less than equal to mid, or j less than equal to high becomes false. Any one becomes false, that means that array is completed, and we come out of the while loop. So just let me quickly trace this one. Then you can look at the video later for tracing part. Now, then what happens is at the last stage, now mid has crossed H. H has crossed mid. So this condition becomes false. So while loop is not executed. And all the elements of left subarray is completed. Right subarray, there might be elements left in the left or the right subarray. So if H is greater than mid, that means H crosses mid, that means left is over. Now copy all the elements from J, K equal to J, we are using a for loop, J to high at the end, all the elements into the array B and increment I. Else what happens? That means else J is high, crosses J. So copy all the elements from left subarray into array B and increment the index. So once this is completed, copying remaining elements, what is left is we are left with the array B. Now this array B has sorted elements. All these sorted elements now have to be copied back into array A. So for doing that, we use a while loop. We use a for loop for k equal to low to high. So k is initially pointing to index 1. For k equal to low to high, copy all the elements from B of k, this B of k into A of k. So once this is done, we will be having the entire thing in sorted fashion. So this is how we try to merge. Using merge algorithm, we try to merge two sorted arrays into a larger sorted array. And this is the main merge sort part. And now we will look at the complexity of this merge sort. Merge algorithm, not merge sort, merge algorithm. Before moving further, we'll look at the complexity of the merge algorithm. The complexity of this merge algorithm, this is the while loop. How many times this while loop will run? It will run till H is less than equal to mid, or J is, it will run until H becomes greater than mid. That is, H is greater than mid and J is greater than high. So assume that in first subarray they are n elements. Second subarray also they are n elements. So we say n by 2, but assume at most, maximum, we call n by n itself. So this while loop will run for n times. Then in this, these are if statement, primitive statements inside, but inside if statements we have a for loop. So this for loop also may run for n times. This for loop also at most will run for n times. Then copying the elements back into array also runs for n times. Now remember, these are not nested loops. They are individual loops. And each one is running n times. So total it is 4n. So the polynomial or function f of n, if we say f of n equal to 4n. 4 is a constant. We can remove 4. And we can say that the time complexity of this merge algorithm is O of n. Not merge sort, merge algorithm is O of n. Now comes the next part of merge sort itself. So we have seen how to conquer, how to actually combine. We have seen how to combine, merge. Now let us look at the merge sort. Merge sort is very simple algorithm. Merge sort takes two parameters, low and high. Low is the first, initially it will be index 1, high will be index n. If low is less than high, that means problem is large. So we compute the mid index. Mid is low plus high by 2. Then we perform merge sort on low, and instead of high, we pass mid. That is, we are performing merge sort on left subarray. And again perform, successfully perform. This is not either, it is successfully. We are performing merge sort on left half of the array, left subarray, perform merge sort on the right subarray. Instead of passing low, we pass mid plus 1. Mid plus 1 to high. High is the last index. Why are we using mid plus 1? Not mid. Here we used low equal comma mid, and instead of low, we are using mid plus 1 comma high. Why are we not using mid comma high? Because the subsets or subproblems are non-overlapping. They don't overlap. So that is why from low till mid is one subarray. From mid plus 1 till high is another subarray. So that is why we have low comma mid and mid plus 1 comma high. In binary search, we made mid minus 1 and pass mid plus 1. Here we cannot use mid minus 1. If you use mid minus 1, that mid element will be left out. It will not be sorted. So that is why, since the array has to be divided, problem has to be divided into equal subproblems. That is why we are using mid and mid plus 1. Now, once this merge sort is recursively called on the left subarray and right subarray, that is the conquer part, we see in divide, that is mid equal to low plus high by 2. Conquer part, we are left with combine, the merge part, combine part. So once these merge sorts happens, ultimately we will call the merge. This is the merge algorithm that we have already seen, passing low, mid, and high indexes as the parameters. So actual merge sort is very simple, 3 or 4 lines of algorithm. Merge sort, we can implement or accomplish merge sort, but actual thing lies in merge. That is the algorithm we have seen here in this slide. A previous slide, we have seen this algorithm. This is the heart or main computation part. Now let us look at the time complexity. Let us quickly solve the time complexity. This is the divide part. We divide it. Check this divide. We call merge sort, passing merge and mid plus 1, then performing merge. Now let us quickly look at the time complexity of this merge algorithm. Now, merge sort algorithm. Now here also we will construct the tree. If you look at this tree, what we have is low is less than equal to high. In binary search, we constructed the tree using the mid values. Here also we are trying to do the same thing. We construct the tree. Here you can find 1, 6, that is low and high. So these values are low and high values. So nodes are not having mid values but low and high values. So this is the actual green is after performing merge. So we have 1, 6 is divided into 1, 3, 4, 6, divided into 1, 2, 3, 3. 4, 6 is divided into 4, 5, 6, 6. 1, 2 is divided into 1, 1, 2, 2. 3, 3 is as it is. There is 3, 3. Low is 3, high is 3, means there is only one element. That we have found that solution. Then 4, 5 is divided into 4, 4, 5, 5. Now, 1, 1, there is only one element, that is 31. 2, 2, there is only one element, 84. This one subset, they contain only one element, both are sorted. Merge them. That is what is the merge algorithm. Merge them. When we merge them, we get it 31, 84. Then at this stage, 31, 84 are sorted. 3, 3 only one element, 57. So this is sorted, 1, 2, 3, 3 is sorted, so merge them. When we merge them, we get 31, 57, 84. Then to the left side, to the right side, we have 4, 4. 4, 4 is only one element, that is 96. At index 4, we have 96. 5, 5, 63. At fifth index, we have 63. So these two are subsets with only one element. Merge them. They are already sorted. When we merge them, we get 63, 96. Then 6, 6 is 25. Here we have 25. Merge them. Both are sorted subsets. Merge them to get a sorted set. 25, 63, 94. So at this place we have two sorted sets. So merge these two of them. We get the result at 25, 31, 57, 63, 84, and 96. So this is how the merge sort, if you divide this, the recursive part of merge sort, when it is called, the left side is completed first, then the right side is completed. And simultaneously, when we are combining, we are joining and getting the result. So this is how merge sort works. Now let us look at the merge sort. Merge sort is the recurrence. It's recursive algorithms. We need to find recurrence relation. Let us assume T of n is the time complexity for the merge sort. Assume T of n is the time complexity for the merge sort. Now, this merge sort T of n, n is the size of the array. If low is less than high, that means problem is large. And problem is, if problem is small, that means n is 1. So if n is 1, time is complexity 1 itself. It's a unit time to compute because this will be only one element in the array and you don't have to do anything, it's already sorted. Then if low is less than high, otherwise that is n greater than 1. We compute mid, it's a trivial part because it takes only unit time to compute. Then we have merge sort. This merge sort, we are dividing the array into 2. So if merge sort takes n as the input, recursively calling this merge sort at this stage, passing mid means we are dividing it by 2. So n divided by 2. So this takes T of n by 2. Then again to the right subarray, we are again calling merge sort. This also takes the rest of the half of the elements. So T of n by 2. And then we have merge. Merge we have already computed. It takes n times to compute. O of n times to compute. Now, if you compare this with binary search either gets called recursively on the left or the right. So we take T of n by 2 only once. But here we have to call the merge sort on the left as well as on the right subarray. So that is why here merge sort is takes T of n by 2 and here merge sort takes T of n by 2. So if we sum up, if n is greater than equal to 1, then if we sum up these things, we have 2Tn by 2 plus n. This is the recurrence relation. Now we will quickly solve this recurrence relation because you've already seen in the earlier stage of binary search how to compute. The only thing is we have 2 over here. Tn by 2, 2Tn by 2. There we had only Tn by 2. So we found the first equation substituting n. The first equation, the original equation itself. Second equation, n instead of n, we substitute n by 2. So it will be n by 2 plus, T of n by 2 equal to 2T of n by 4. This 2 remains as it is. This is 2. We cannot substitute anything over here. It's 2. Only in place of n, we are substituting n by 2. And here it is n. And in binary search, we had 1. Here we have n. So instead of n, we substitute by n by 2. Then same way for n by 4. What happens is we have T n by 4 equal to 2T n by 4 by 2. So it becomes n by 8. N by 8 plus. Instead of n, we have n by 4. That becomes our third equation. Then fourth equation is instead of n, we are substituting n by 8. So here 2T n by 8 by 2, which is n by 16 plus instead of n, we substitute n by 8. So this becomes our fourth equation. Now let us successfully substitute these things. So here we have 2T n by 2 plus n. So instead of T n by 2, we are substituting 2T n by 4 plus n by 2. So 2 into 2T n by 4 plus n by 2. So what happens here is this whole thing, 2 multiplied by 2 is 4T n by 4 plus this 2 and 2 gets cancelled. So this is n plus n. So we have n plus n. Then instead of, so this whole equation, instead of Tn by 4, we will substitute it with 2Tn by 8 plus 4n by 4. So this 4 is over here 4, and instead of Tn by 4, we are substituting 2Tn by 8 plus n by 4. So what happens? This becomes 8Tn by 8, 8Tn by 8, plus this 4 and this 4 gets cancelled. So we have n itself, plus n plus n. So we have 3 n's. Same thing, it's t, instead of Tn by 8, we will substitute by 2Tn by 16 plus n by 8. So here we have 8 multiplied by 2Tn by 16 plus n by 8. So 8 gets cancelled, and this is 2t is 16. So 16Tn by 16 plus n plus n plus n plus n, successive n's. So if we compute this, I mean if we substitute this recursively for the ith time, this is 2 power 2. Actually, this is 2 power 1, 2 power 2, 2 power 3, 2 power 4. For ith time, it will be 2 power I. Then t of n by 2 power I, because 2 power 2, 2 power 2 power 2, oh, sorry, 2 n by 2 power 1, n by 2 power 2, n by 2 power 3, n by 2 power 4, till n by 2 power I, plus first time n is 1, second time n is 2, third iteration, third time n is 3, fourth time n is 4, ith time n will be I multiplied by n. So we substitute for the ith time, we have this as the relation, this as the expression. Now let us solve this expression. Now this part, n by 2i, if it is equal to 1, we know that it is constant time. So when n equal to 1, the time is 1. So t of 1 means n by 2 power I should be equal to 1, which is nothing but equal to n equal to 2 power I, which is nothing but I equal to log n base 2, log n base 2. Now let us substitute these 2 power I as it is. Instead of t of n by 2 power I, we said that it becomes 1. It reduces to 1. So that we have a solution. So t of 1 is 1 itself. T of 1 we are writing. Plus I multiplied by n. Now t of 1 is 1. So 2 power I multiplied by 1 is 2 power I plus I multiplied by n. Now what is 2 power I? Because this whole expression now has to be written in terms of n, not in terms of I. The time we found it and we have reduced it. This whole thing has to be written in terms of n. So 2 power I, what is 2 power I? 2 power I is nothing but n, is equal to n. So we say n plus, what is I? I is log n. So we have log n multiplied by n. So this expression becomes n plus n multiplied by log n, which is nothing but asymptotically t of n, or time complexity of merge sort, is equal to O of, actually this n log n is the highest polynomial. So the time complexity is O of n log n for merge sort. So this is what was all about merge sort. Remember, merge sort has got the time complexity in worst case as O of n log n. So this is how divide and conquer approach. Using divide and conquer strategy, we can divide the number of elements into different subsets, recursively sort those subsets, or call merge sort on that subset, and finally combine sorted subsets into one and perform the merge sort. So we have seen merge sort, how it uses divide and conquer approach. We have seen the algorithm for the merge sort as well as merge algorithm. And then Using the recurrence recursion, we have computed the time complexity of merge sort. Now, before we end, the important point over here is when merge sort is asked in the exam, you have to first write this algorithm, that is the merge sort algorithm. You have to write this algorithm, then also write the merge algorithm. Without writing the merge algorithm, merge sort is not complete. So this is the merge algorithm. So you also have to write. You have to also write the merge. So merge algorithm. Theoretically explain, but if it's specifically asked about algorithm, you have to write an algorithm. Merge, sort, and merge. Both these algorithms you have to write. And if it is just asked theoretically, you write the algorithm and just say that time complexity of merge algorithm is O of n, and the overall time complexity of the merge sort algorithm is, in the worst case, is O of n log n. You don't have to use recurrence relation to compute and solve and show that it is O of n log n. But suppose if the question is asked to solve so and so recurrence relation, or with the using the recurrence relation, compute the time complexity of merge sort, then only you try to write this. Otherwise, don't try to use merge sort and solve the recurrence relation. Okay. Theoretically, it is asked merge sort, write merge sort algorithm, write merge algorithm, describe in some theoretical part, just state the time complexity. If the question is asked to use the recurrence relation and derive the time complexity, or show using recurrence relation the time complexity of merge sort, then write the recurrence relation and solve recurrence relation and show it. Otherwise, there is no need. So this is what we have it. Actually, I have, I don't know, I just, it's 1:30 now. I suppose we have not overlapped with any of the other class. I don't think so. You have any classes in the afternoon, so I don't think so. We have overlapped. Now I have to stretch it because several times we got disconnected. So that is the reason we have to stretch it along, and this is topic completed. In the next class, we will try to look at the quick sort algorithm, which is again one of the most important. Merge sort and quick sort is one of the two most important things in divide and conquer, and actually in sorting itself. Now, if you have any questions, let me clarify. Otherwise, we will again meet in the next session. On Thursday, I suppose. So if there are no questions and all, then you can log off, and we will meet in the next session.